Hi everyone, welcome to Acid-Base Equilibria 1. Turns out that all acid-base reactions involve an equilibrium. Okay, it's kind of a unique one, so we kind of look at it in some detail. This is the kind of underlying theory behind buffers, which we'll get to later. Okay, now a couple of kind of quick common sense things. So this is stuff we probably already know. It's not actually covered super well in Chemistry 101, although it is covered in Chemistry 100, interestingly, okay, because we kind of saved the acid-base stuff to 102, okay? So you probably have kind of a vague idea maybe of acids and bases, but this will kind of fill in all those details. And if you remember, I did kind of talk about acids and bases a little bit, working at pH, things like that, in the last pre-lab, okay? So you already have a little bit of background knowledge. Okay, let's take a look. So first things first, what's an acid, what's a base? Give some examples, right? So if I go generic, right? Acid, okay? What do acids do? Well, they increase the amount of H plus aqueous ions in solution, okay? So the more H plus you have in solution, you probably know the more acidic a solution is, okay? So acids, generically, okay, have the formula, you know, H on the front, whatever, anion on the back, okay? So acids increase the H plus ion concentration. They do so through dissociative dissolution. So if you remember, like dissolving NaCl in solution, it breaks into its ions, right? Okay, so acids break into their ions. H plus on the front, anion on the back, okay? Bases, kind of the yin and yang of the universe, okay? The kind of opposite chemical, if you like, of an H plus is an OH minus, acid, base, like yin and yang, right? Okay, so OH minus, anion, so it doesn't matter what's on the front, usually a metal ion like Na plus or something. So some kind of metal on the front, OH minus on the back. Again, undergoes dissociative dissolution to make OH minus ions in solution. So bases very simply increase the OH minus ion concentration in solution. Fair enough. Now some examples. HCl is stomach acid, right? Okay. Stomach acid dissolves to give you H plus and Cl minus. Okay, so just by dissolving that chemical in water, we make H plus. More H plus is acidic. Fair enough. Okay, so sodium hydroxide. Sodium hydroxide, actually, you've probably seen this. It's a solid. Turns into Na plus OH minus. Okay, there you go. So that's two strong materials, strong acid, strong base. Okay, now the picture. Okay, this is fish and chips, right? So I'm from England, so I eat fish and chips. And what do you put on your fish and chips? Salt and vinegar, right? Makes it taste good, yeah. But you don't sprinkle HCl on your fish and chips because that will kind of dissolve the paper in the fish and the chips, right? You actually put acetic acid, aka vinegar. Now remember we had this kind of generic here, okay? So what, I can't even see the bottle, it's on the counter somewhere, right? So on the counter they got some vinegar, yeah, and the vinegar is, now do it in the generic way. So H plus is the acidic proton, that falls off, right? And then the counter ion is C2H, let me get this right, 3O2. So that's the acetate ion, right? And that's the H plus ion. Now that's a weak acid. We'll get into details later, okay? That partially dissociates to make a little bit of H plus and that counter ion. Now here's the thing. I know there are H's in that molecular anion, okay? But keep them in the anion. What stays in the anion, right? Stays in the anion. That makes sense. Okay, so what happens in the anion stays in the anion. That's, yeah, okay. This is the acidic proton. This is the one that falls off. These guys stay intact as a molecule, okay? So we write them as dissociated. So in other words, think about the generic. Whatever's on the front comes off. Anion is a molecule, right? So it's not just a Cl minus or something. It's a molecular anion, right? Okay. So we get to this meaning later. This means it's a weak acid. We have an equilibrium, so we make less H plus. Meanwhile, with a strong acid. Okay, all right. Now, definitions. Okay, so we've got to be a little bit careful about how we define things. Yeah, okay. There are many ways to define acid and base behavior. Some more useful than others. Okay, depends on your application a little bit. Okay, but they're basically, no pun intended, there are three models. All right. So Bronsted, Arrhenius, Bronsted, Lowry, and Lewis. Okay, so the Arrhenius is the one probably we're all familiar with. We just talked about it. An acid that's an Arrhenius acid increases the H+ ion concentration in water. So that's, you know, everyone's common definition. Okay, we go into the others as we go. Okay, an example, of course, would be, well, we did it already, HCl. Obviously, we've increased the amount of H+ ions in solution. Okay, Arrhenius base then increases the amount of OH-. We do the same one again. All right, I'll write it in as well. Increases OH- ions concentration in solution. Okay, all right. So there we go, nice and simple to start. Okay, we'll talk about the subtle differences between strong and weak acids as we go, but for now, just remember that acids increase H+ ion concentration, bases increase OH-. Okay. Oh, interesting. I showed you some pictures of some Scottish people there, right? It turns out Scotland has the highest rate of heart disease in the world, okay? Because they eat fish and chips at least twice a week. It's kind of the standard. People go to McDonald's here, which isn't so great, but fish and chips kills you quicker, okay? So be careful with fish and chips. Once in a while treat, okay. Now, so Arrhenius is just increasing H+ in solution for an acid, increasing OH- for a base. But then we look at the kind of the underlying mechanism, how that happens. And to be honest, Arrhenius explains everything generically, okay? But if you kind of pop the hood and look at how the certain models work, one is a proton transfer model, right? And the other is a lone pair model, which we'll get to, Lewis, okay? So there are two ways to think about how that increasing H+ or increasing OH- actually happens. So pop the hood, look at the mechanism. Bronsted, Lowry, proton transfer. So we concentrate on proton donors. If you think about it, hey, a proton donor would be an acid, right? It increases the amount of H+ in solution by, you know, letting it out, right? So HCl dissociates, H+ goes into solution, it's more acidic, okay? So, but before we get there, some very, very important things, right? So real quick, we write this all the time. We write this all the time, don't we? That's a complete lie, right? That does not exist. Although we write it, it's kind of a known thing amongst chemists that it's kind of a trick, right? There are no such things as naked H+ ions. Now think about that for a second, right? Think about that for a second. What is an H+ ion? Well, it's hydrogen that's lost an electron, right? Hydrogen is element number one electron, one proton. So if you remove that electron, it's just a naked proton, right? So that thing is super, super, super tiny with a relatively large charge, +1. So it would be massively polarizing. It wouldn't actually be stable in nature, okay? So there are no such things as kind of independent protons wandering around, which would be H+ ions. They actually have to exist in a more stable form, and that's the hydronium ion, right? So what happens with the hydronium ion is you get some H+ ions, right, which we'll come on to later, okay, how this works. But basically, it jumps onto a water molecule, right, to make this. That's the H3+ ion. So think of the water molecule a bit like a ferry boat and the H+ a bit like a passenger, right? So the water molecule ferries H+ around and drops it off where it needs to do the chemistry, and that's called the hydronium ion. There's a better picture right there, okay? So it's more appropriate to write H3 plus O as the actual thing in solution that causes acidity, right? But we always, in practice, because it's just shorthand, call it H+ aqueous, okay? But remember, there is no such thing as H+ aqueous. It's actually H3O+ hydronium ion, Okay, so if you think about that, there's some kind of interesting side effects to that, right? So if you think about it, can a completely dry acid, so HCl, vinegar, citric acid, something like that, is that in any way activated? Is it harmful, right? So if you put your hand, assuming you could have a completely dry hand, right, which isn't possible, but say you could, right? So if you put your completely dry hand into pure HCl, would it hurt you? Never try this because we're always a little bit wet, right? The answer is no, because acids need water to work. Okay, have you ever tried those really, really sour candies? There they are, right? They actually have pure citric acid sprinkled on the outside. And you can handle these things. You don't get a chemical burn when you handle the sour candy, do you? But when you put it in your mouth, it tastes super sour because the acid comes into contact with water. The H plus can transfer. It can inactivate. Okay, so bottom line is acids need water to work. You have to make the hydronium ion H3O+. Okay, so let's just write a few facts down. So acids need water to work. A powdered pure acid, assuming it stays dry, is harmless. Think of citric acid powder on gummy bears, right? There's no kind of chemical warning in the sweet shop. Okay, all right, because you make H3 plus O. You have to make hydronium ions to make an acid work. All right, okay. However, I shouldn't be kind of blasé about it, okay? Because if you think about it, we are mostly bags of water, right? I think that's a Star Trek quote, right? Bags of mostly water. Yeah. So when we come into contact with acids, we actually make them wet just by handling them. So unless you're wearing gloves, it's kind of tricky, right? So they're not safe to touch because we ourselves are moist. Like if you breathe in HCl, that would kill you, right? Because HCl gas gets into your lungs, immediately turns to a strong acid and you're dead, right? So be safe, be safe around acids. Remember, we ourselves, are a little bit wet, right? So when we kind of interact with things, we make them wet. So be careful. Not safe. Humans, I hate this word, but we'll say it. Humans are moist, right? So think of your lung lining, etc. All right, so if you happen to breathe in a gaseous acid, HCl, or even sulfur dioxide, right, which can dissolve in water to make acids, right, it's very, very dangerous. Okay, and I actually did that once. I didn't clean up an experiment once. There was some SO2 and a fume hood. I breathed it in, and it really stung. Okay, so be careful around acids because we ourselves will activate them just through touching them because we're not perfectly dry, are we? Okay. Okay. Turning over. So we talk about this proton transfer model. It's like those you see those people on the street with the shells with the P underneath and they're moving it around. Okay. It's a bit like that, right? So instead of keeping your eye on the P, keep your eye on the H plus ion, right? Okay. So an acid gives away H plus ions, right? Okay. So Bronsted-Lowry acid are proton donors, right? They give away H plus. Bronsted-Lowry bases then are proton acceptors. So if you get that simple idea straight, proton donor is the acid, proton acceptor is the base in the Bronsted-Lowry model. Okay, so if you were to dissolve some HCl in water, so there's HCl, which actually comes in the gas phase, so it's like a Lewis, right? So there's a Cl and an H plus, right? Okay, that's an H plus donor because there's water, right? And what's going to happen is it's going to make that kind of ferry boat situation with the hydronium. So this is going to come off and jump on here, right? And that's exactly what we get over here, okay? So water has accepted an extra proton, okay? HCl has lost a proton. So because it's lost, it's a donor, right? If you give something away, you donate, yeah? So the H plus was donated from here to here. H plus was accepted from here to here. So that's a donor, Bronsted-Lowry acid. HCl is an acid, we know that. H2O, glass half empty, glass half full. It's interesting, when we do acid bases, there's always an acid, always a base, right? In this model, water would be the Bronsted-Lowry base because it accepts a proton. It's H3O plus now, not H2O, right? So obviously it accepted. So you can just look at the formulas. Hey, there's one less H plus in the formula, it must have donated. There's one more, it must have accepted. Okay, so water is a Bronsted-Lowry base. Anything that gives away protons, it could be citric acid, nitric acid, whatever it is, anything that, our classic acids will be proton donors. Okay, so here's a little trick. So all you have to do to figure out what's what is just look at the formulas and say, hey, who's got one more, who's got one less? H plus, right? Okay, so if we look at the first one together, and you guys can do the other two, right? So if we look at NH4 and its kind of counterpart over here, which we'll get to later, called conjugates, right? But anyway, we'll get to that in a moment. So identify the Bronsted-Lowry acids and bases. So NH4 plus turns into NH3, so it lost, right? So that's a Bronsted-Lowry acid, Bronsted-Lowry base. Hey, this guy must pick up that. So that's a Bronsted-Lowry acceptor base, Bronsted-Lowry acid. Okay. That makes sense? And these are pairs, right? So the acids go with the bases, if that makes sense. So the acid turned into a base because it lost a proton. The base turned into an acid because it gained a proton. If we had the reaction in reverse, same idea, right? We just switch the definitions. Okay. So try these other ones. Look at these, okay? This one here is actually interesting, right? It's somewhat related to your lab, not super intimately related to your lab, but somewhat related to your lab. Okay, so here we have the hydrogen sulfate, hydrogen carbonate. Look over here, who lost, who gained? Then go ammonia and water. Hint, hint, ammonia is a base, right? We use it in lab all the time, so hopefully we'll see that in the equation. Okay, let's look here, right? Now this is interesting because these are both, and we'll see it later, they're both capable of both acidic and basic behavior. They can gain or lose protons, but it's kind of who's a stronger acid will be the one that loses the proton. So let's look over here. SO4. So SO4 lost the proton, so that's acid. That's then the base, right? Because that becomes a base, that becomes an acid. Okay, that makes sense? Actually, you don't really need to label the right-hand side. We'll get to that later. It could be a little bit confusing right now. So let's just keep it on the left side. This is an acid because it lost a proton. This is a base because it gained one. Okay, we'll talk about conjugates as we go. All right, last one. Hopefully you got it. Okay, NH3 becomes NH4, right? Water becomes OH minus. Hey, this lost, right? So that's the acid. And that must be the base because it gained. Yeah, so ammonia is a base. So when you dissolve ammonia gas in water, the water becomes alkaline because you make OH minuses, right? It's a base, yeah. So ammonia, it's interesting, it doesn't dissociate to make OH minus. There are no OHs in ammonia, right? So it kind of jump out like you would in NaOH, for example. It actually reacts with water to make OH. So ammonia plus water turns into ammonium and OH minus. Interesting. All right. So it satisfies the generic definition of what a base is. All right, now, as I mentioned, the things on the left and the things on the right are what we call conjugate pairs. So I kind of jumped ahead just a little bit there. Hopefully that wasn't confusing, but let's talk about it, right? So acids and bases, so whatever's an acid on the left, what's left on the right is its conjugate, right? And if it's an acid on the left, in a reverse reaction, it would act like a base. Okay, so let's look at that in some detail, right? So in an acid-base equilibrium, the acid donates a proton, right? And the other reactant accepts, so it's a base, yeah? And what's left, if you think, when that process happens is called the conjugate, right? So here we have a generic, right? This might be HCl or something like we saw before with water. So the acid that is lost, right? And there it is, it's gained, yeah? So acids have a conjugate base, yeah? So what's left when I remove the H plus is the conjugate base. And the base has, I add that H plus, a conjugate acid. Because in the reverse process, why is it called conjugate acid base? Because in the reverse process, this would act like an acid, right? To make this. This would act like a base to make this. So in the left to right direction, this acts like an acid. In the right to left direction, oops, it acts like a base, and vice versa. Okay, so we always have acids and bases, and our definition is always left to right, usually, right? Okay, so in the left to right direction, we have acids and bases, which turn into, when the process of transferring that proton occurs, conjugate base from the acid. So I've lost my proton, that's the conjugate base, and conjugate acid from the base, okay? Now remember, this is all equilibrium, so reactions can go in both directions. If I went the other way, the base would pick up a proton to make this, so it acts like a base. H3O plus would lose an H plus to make this. So in the other direction, these act as acids and bases respectively, okay? In the left to right, these act as acids and bases. So hopefully you got that right, okay? Now here's a bad dad joke, okay? If HX goes to visit X minus, is that a conjugate visit? Go down to the jail, conjugate? That's a bad joke, all right? So, we have forward reaction acid-base pairs, or acid conjugate base pairs, and conjugate base acid pairs, okay? All right, remember the word conjugate always appears on the right, and it's the opposite. So an acid turns into a conjugate base, a base turns into a conjugate acid. So, kind of defines the direction of the reaction, doesn't it? Okay, so here's, I think that's nitrous acid. Okay, so HNO2 plus water turns into NO2 minus and H3O plus. So obviously this lost, so it's now a base, but we call it a conjugate base. This gained, so it's a conjugate acid. So base turned into a conjugate acid, acid turned into a conjugate base. Okay. Task. If that reaction was reversed, let's identify the components, right? So if I had this one instead, right? So if I had NO2 minus, so it's the same reaction, I'm just writing it in reverse, right? Glass half empty, glass half full, right? So which one's an acid? Well, this one's an acid because it makes something with less, oh, sorry. Okay. So I've written it in reverse, okay? So it says identify the acid-base pairs for the reverse reaction, right? So all I've done is switch this around, right? So now I'm going traditionally from left to right. So I'm going to say, which one's the acid? Well, the thing that loses a proton. Well, it's this guy here, right? Acid. That's the conjugate acid. Sorry, conjugate, base, right? Here, this must be the base because it picks up to make conjugate acid. There we go. All right. So remember, equilibrium are all relative, right? So reactions typically go left to right, but you can also go from right to left because you have measurable amounts of reactants and products at equilibrium, okay? When we have a single arrow, remember, that's kind of like a very large K, right? So it's pretty much all left to right when we have a single arrow. But when we have double arrows, which most acid-base equilibriums are, there's going to be some of each present, right? So, you know, think about the definition, left to right. Whatever you write down on the left is acid and base. Whatever you write down on the right is going to be the conjugates, right? So that's what I've done here. That I switched the reaction around, yeah, but I'm traditional left to right, so acid and base conjugates. Okay. Oh, an assignment. Okay. All right. So this is, you know, in class what we would do a workshop, right, where we would sit in small groups and we'd solve these problems as little groups, right? Obviously, that's not possible. So what I suggest you do is, you know, pause me, right? Pause me and just try this, okay? And I'll come back in a second and solve it. Okay. You back? All right, so let's take a look. So we can go kind of first principles, right? So let's look at it. Identify the acid conjugate base and base conjugate acid pairs, right? So let's just, I like to look at acids, right? So which thing lost an H plus? Well, there's nitric acid and there's nitrate, right? So that's the acid. That means that's the conjugate base. That must be the base then because it gains, it does. Conjugate acid. So hopefully that made sense. Okay, A for acid, B for base, CB for conjugate base, CA for conjugate acid. Here's our classic ammonia again. We saw that one already. So if we had a flashback to that kind of previous slide at the start where I kind of jumped the gun a little bit, here it is, right? So ammonia and water. Well, ammonia, it gains an H plus. So that's the base, right? Bases gain H plus. That means that's a conjugate acid. That must be the acid. Why? Because it lost an H plus. There we go. All right. Now, interesting, ammonia is pretty much what we call a weak base, right? So under equilibrium conditions, there are actually more reactants and products here because it's not a strong base. In other words, the concentration of OH isn't very high. When we get onto the equilibrium constants or acids and bases, Ka and Kb we call them, we'll see that in more detail. But you know, Weak acids, weak bases, less product, okay, because it's an equilibrium. Strong acids, strong bases, almost 100% product, stronger chemicals. All right, what are the conjugate bases? Now be careful here, right? So conjugate base, let's just look up here as an example, right? So H2O acts like an acid and you make a base, right? So the conjugate base is a proton less, right? Okay, so what would be the proton less for this guy? All right, remember we lose a proton, so it's not H2, it's H1, and we lost a plus, so we gain a minus. Hopefully that makes sense, right? If you do that kind of same logic, HS minus, HSO3 minus, and this one, CO3, 2 minus. Okay, all right. Conjugate acids. Now the acids, if we go up here, okay, acids have gained, right? So we're going to gain protons. So H3PO4, we gain an H plus, we lose a minus. Oh, sorry, up we go. We gain an H plus, we lose a minus. Feel free to pause me, right? There we go. Hopefully that makes sense. H3PO4, HSO4 minus, the hydrogen sulfate ion, hydrogen cyanide, carbonic acid, hydrogen carbonate. Okay. Again, it's like an accounting thing, right? As long as you got the definition correct, okay? Acids lose protons to become conjugate bases, right? Okay. If you remember that one, you can kind of do the reverse for bases. All right. Now, interesting. If I go back, if I circle that one, and I circle that one and that one, right? We can see that some chemicals can act both as acids and bases, okay? So HCO3 here turns into CO3 2-, okay? So it acts like an acid. Here, it turns into H2CO3, so it picks up a proton, it acts like a base, okay? So it's interesting, so those poly polyacids we call them, right? So H3PO4, H2SO4, H2CO3, they can lose 1, 2, sometimes 3 protons. They can have sequential dissociation, right? But I kind of stop halfway through. I can either keep going to lose or I can go back to where I came from to gain, okay? So amphoteric behavior, and that's what amphoteric is. Amphoteric behavior is when we have something like, classic is an easy one. Let's do this one. HCO3 minus, right? I can minus an H plus and go to CO3 2 minus, or I can gain an H plus and go to H2CO3. So some partially deprotonated polyacids, right? H2CO3, H2SO4, H3PO4 can go either way from the partially deprotonated, right? So that's called amphoteric behavior. In other words, they act as both acids and bases, okay? So dihydrogen phosphate is similar, right? But because there are 3 protons that can come on and off, it's actually got more steps it can go through, if that makes sense, okay? So amphoteric behavior, act as an acid or a base. Acids lose H plus, bases gain. So, you know, things like this could lose 2 or gain 1, couldn't it, right? So we can go through that kind of sequence, all right? So let's just try these tasks, right? Maybe I'll do the first one. You guys can, oh, I've got literally 9 seconds left. Okay, so I'll come back in a second. All right. All right, so we're talking about amphoteric behavior. Things that are amphoteric can act as acid or bases. They can either gain or lose H plus ions, right? Okay, so write an equation for the reaction of H2PO4 minus with water in which it acts as an acid. Okay, so H2PO4 minus reacts with water as an acid, right? So it's going to do what? Lose, right? So it's going to turn into 1H because it's going to lose PO4 2- plus the hydronium ion. Remember, that's the, the thing that's really responsible for acidity, okay? Why don't you guys try B, right? So write a similar equation, but when it reacts with water in which it acts as a base. So it steals a proton from water. You got it? So H2PO4 minus plus water, that's going to steal a proton, right? So I'm going to get H3PO4 plus OH minus. And as you can see, these reactions result in the formation of hydronium ions, that's acidic, and OH minus ions, that's basic. So amphoteric behavior, we're increasing the concentration of H plus essentially and OH minus, you know, through amphoteric behavior. Okay, both ways, right? Now what you can do, it's interesting, and I kind of showed you this up here a little bit as kind of an intro. You can kind of write these kind of chains out where you kind of sequence it, right? So if I have H3PO4, and we do the whole thing, right? I can lose an H plus, right? And I can turn into H2PO4 minus aqueous. If I take H2PO4, I can go back the other way by adding, right? So there we go. I can kind of go backwards between these two, yeah? But hey, I'm not done because I can do the amphoteric behavior with this again, right? So I can go HPO4 2 minus H plus H plus. And finally, I can remove that last one, PO4 3 minus an H plus an H plus. So obviously the more H pluses the polyproton acid has, right? I almost said polyprotonic, which sounds a bit Star Trek, but no. Okay. So I can lose consecutive protons all the way down to the naked anion, or I can add protons all the way up to the fully protonated acid. Okay. So if you think about it, both of those are amphoteric. Okay. At the end here I can only go one way, so that's not amphoteric. At the bottom here I can only go one way, that's not amphoteric. But these guys in the middle are fully amphoteric. Okay. All right. What I suggest you do is try hydrogen carbonate. Hydrogen carbonate, as we'll find later, is super important in the human body. It's the thing that regulates your blood pH. We'll talk about buffering later. And how does it do that? Well, it's because it's amphoteric, it can go both ways. Okay. So if I have that in my blood, I can either remove an H plus if there's too much H plus in my blood to make carbonate, or if there's not enough H plus in my blood, I can add. Sorry, if there's too much in my blood, yeah. So if you think about it, that would actually liberate H plus, wouldn't it? So if I go from hydrogen carbonate to carbonate, I'd make H plus. So if my blood's too basic, I'd do that. If my blood's too basic, if you like, I can release, I can remove H plus if the blood's too basic, yes, to make this. There you go. All right, so that's the H plus in your bloodstream or not in your bloodstream. Okay, we're going to, that's the concept we're going to later, because a buffer is basically modifying an acid-base equilibrium like this. Okay, that's what a buffer is. Okay, we'll talk about math of buffers later. All right, now we're at an interesting spot because, give you kind of a quick history lesson here, where as I record this, it's Wednesday of spring break. And if you remember exactly 1 year ago, if you're at JJC exactly a year ago, you went to class as normal until spring break, and then the whole COVID thing happened, right? So we then started teaching exclusively online from spring break onwards, and we have been doing ever since, okay? So from this point forward, because I was teaching a year ago, I was teaching Chemistry 102, from this point forward I actually have videos I already made. So what I'm going to do, instead of re-recording all those videos, technical difficulties, right? So instead of re-recording those videos all over again, I'll show you the same videos because the content's just the same, but what's slightly different is just the camera position, okay? And what I'll do, I didn't have a picture-in-picture, so what I'll do, I'll watch the videos over kind of with you, like a reaction video, like I'm Lucy Liu or something. You gotta go look that up. All right, so I'll watch the videos with you and I'll kind of pop up in the top right-hand corner if, I need to say something about the video or what's going on the page. But generally speaking, there won't be an insert of me there when you watch the remaining videos for the semester, unless I need to make a correction or comment on something. As I mentioned, the content is exactly the same. It was just recorded a year ago before I got all the bells and whistles with the picture-in-picture sorted out. Okay. Now, if it gets to the point where you really don't like the old videos, or and there's a kind of a groundswell of kind of just, what's the word I'm looking for? Discontent, right? If you're not liking the videos, just let me know and I'll go back to making them like you've been having them for the first part of the semester. But to be honest, I think it's going to be pretty much business as usual. All right, stop there, and I'll see you guys in a minute. Talking about the relative strengths of acids and bases, we're mostly going to focus on acids. That's the main focus of the class. But what applies to acids also applies to bases to some degree. Okay, so the question says, and there are some, Scottish people. There are some Scottish people eating some fish and chips, right? Fish and chips is the biggest fast food in Scotland. So why can you sprinkle acetic acid, which is vinegar, about 0.1 molar? That's what it is in the packet or bottle of vinegar. Why can you sprinkle vinegar on your fish and chips and it's really tasty? Well, you probably shouldn't sprinkle 0.1 molar HCl or any strong acid on your fish and chips, because it will basically dissolve the fish and chips, the paper, and maybe your fingers. Okay? It's because of a very simple thing, and it's the difference between a strong and a weak acid. Okay? So a strong acid HCl as an example is 100% dissociated. Okay, so strong acids are 100% dissociated. You start with 100 HCl molecules, you get 100 H plus ions. Remember, the concentration of H plus is what gives rise to acidity, I should say. Okay, now vinegar, and you can check the back of a vinegar packet if you wish, they're called weak acids. Okay, now weak acids, vinegars partially dissociate. That's code for they're in equilibrium. Okay, so something like vinegar, and we'll just do a generic HA, A for anion. Anion is kind of a complex molecular anion for vinegar. It's the acetate ion. Okay, it may be 10% dissociated, meaning that 1 in 10 molecules will break apart. You get a tenth the strength of H plus. Therefore, a tenth the acidity. Okay, so that's why a nice kind of tangy sour taste is due to H plus ions. Too much is a bad thing. A small amount's a good thing, if that makes sense from a kind of a human perspective. Okay, now to look at this, we can do an ICE table we've seen before. Okay, so if I do HCl, okay, and it is in the pure state of gas, so why not write it, plus H2O. So I'm bubbling some HCl through water. What do I make? Hydronium ion, we've seen that one. The true acidic ion. And chloride. ICE. Initial change equilibrium condition. Okay? So, move that up a shade. Initially, let's say, just pick some easy numbers. 100 molecules of this. Kind of meaningless, the amount of water, because it's an excess. And initially when we throw the HCl in there, it's 0. Okay, change, well, it's a strong acid, right? So it's going to be 100 out of 100 will break apart. So we're going to make 100 here, make 100 here. My nice example is, hey, there's 2 passengers in the car. When everybody gets out, 1 guy, 1 girl, if you like. Okay, so 100 pairs. 100 guys, 100 girls. That makes sense with my silly analogy there. So at the end of the day, 100 minus 100 is 0, 0 undissociated, 100, 100. Just think about these as percents. For every 100 molecules, I get 100 H plus ions for a monoprotic. Therefore, 100% dissociated, i.e. strong acid. Now, weak acids, and maybe we'll do vinegar. So vinegar has the formula H, and then I'm going to put C2H3O2 in brackets there. This is the acidic proton, which kind of hangs off the molecule. These are inside the molecule, they stay inside. Okay, so plus H2O again. That's actually a liquid in the pure state. It turns into H3O plus the acetate ion, C2H3O2 minus, aqueous. Same deal, ICE. Oh, I'll pull it up for you. I have to make sure I don't kind of obscure that. So there we go. Acetic acid, water, dissociation products, an equilibrium, so that kind of reminds me to do that. Okay, now initially again, let's say there's 100 molecules, 0 and 0. 10% dissociation is a reasonable number. So 10, my analogy is 10 vehicles stop and everybody gets out. So 10 vehicles stop, 10 guys get out, 10 girls get out. What's left at the end of the day? 90 intact molecules, right? 10 and 10. So that's where we get the 10% dissociation number from. Okay. Now obviously this is governed by dissociation math, which we'll get to. Okay, but you see the point there. All right. So turn over the page. Here's a nice picture of the microscopic view. Kind of hokey, but I'll hold it up to the camera so you can see it a little better. Okay. So on the left there we have a fully dissociated HCl. The big ones, if you like, is Cl minus. The small ones are H plus. 100% dissociated, all individual atomic ions, electrolytes. Okay, on the right side, we see a weak acid. Okay, so we do have a few separate hydrogen ions which are responsible for acidity, but the majority, 90% in our previous example, 90% of molecules are still intact, undissociated. So that's why we call it a weak acid. There's lots of undissociated molecules. Okay. Now, a few things from the slide, okay? One, strong acids, complete dissociation. We see up here, everything split apart. Strong acids, complete dissociation, if you like 100% dissociation. Okay, so when I say strong acid, I mean a mineral acid, something you see in lab, something with a chloride anion, a nitrate anion, anything, if you like, that's not organic. Organic things, molecules, carbon, hydrogen, oxygen. Okay, so those molecular anions are typically associated with weak acids, whereas non-molecular anions, chloride, fluoride, things like that, are associated with strong acids. Okay, so if you think about it, if it's a strong acid, it has a negligible strength conjugate base. If it's HCl, okay, the Cl minus ion is so weak it doesn't pick up H plus to go in the reverse direction for the reaction. Okay, so strong acids are essentially a one-way street. 100% dissociated means essentially a complete reaction. Okay, now in terms of weak bases and acids, weak acids, and you can apply acids and bases together. Okay, so weak acids have incomplete dissociation. They're in equilibrium. Okay, so they have similar strength acids and conjugate base. Similar strength acids and conjugate bases because, of course, they're in equilibrium. So the forward and reverse reactions are of similar magnitude, if that makes sense. Okay, so just to recap, strong acids, complete reaction, negligible strength conjugate base. Weak acids, partial dissociation, similar amounts of acid, undissociated, and conjugate base at equilibrium. So similar strength if you wish. Okay, all right. Bottom line is, it's kind of a reinforcement. Weak acids and bases, always in equilibrium. So therefore, K-math. So when we have weak acids and weak acids or weak bases as a problem, we can always think of the math in terms of an equilibrium constant type problem. Okay, and that's what we get on to. Okay, so special equilibrium math for weak acids and weak bases. All right. Now, here we have, just something I took from the book. it is a table of acid and base strength. If I just bring that up to the camera, maybe closer. Okay. All right. So it's kind of hard to see. I'm battling with the camera a bit. But you have it in the notes in front of you, of course. Okay. So you can see on the left, we have increasing strength acids, weakest at the bottom, strongest at the top. Okay. So perchloric acid is the strongest mineral acid we have, closely followed by sulfuric. Okay. And if we look on the right side, we see kind of the reverse situation, increasing base strength. The conjugate base, interestingly, so if you look at perchloric acid at the top, its conjugate base is on the right, its acid is on the left. So the strongest acid up here has the weakest conjugate base over here. Okay, so it's kind of the same order but backwards. Okay, so at the top is the conjugate base perchlorate ion. At the bottom we have things like hydride ion, hydroxide, and things like that, which are really strong bases. Okay, if you have that league table, remember the more reactive or more chemically kind of stronger material will react in preference to the weaker one. So we can use the slide here to predict if the following equilibria lie to the right or left. Remember, it will move in the direction reacting away stronger material. Okay, so if we look here, what do we see? We see pairs. We see this is a conjugate acid, this is a base. If we go here, it's lost a proton, so that's an acid, that's a conjugate base. Okay, so if we compare acids and bases, we can see which is the stronger. Okay, so if I look at maybe acids first, right? So acid and acid, which is stronger? Let's take a look. Okay, so water, oh, there's water right there. Okay, and hydrogen phosphate ion. So I can find it. Yeah, oh. Not a great example, is it? Let's go to the other one. Let's go with bases. Let's go hydroxide and phosphate. Okay. Hydroxide and not a great example again. I guess I must have looked in the back here for that. I'm actually going to pause here. I'll go and find that information. Okay, so we're back. Apologies for the delay there. Okay, so actually the information I need is actually in the appendix. So you can look in the back of the book there for the appendix. If we look, what do we see? Well, there's our two acidic species, HPO4, 2- and water. Okay, there they are. Which is stronger? This one is stronger. Okay, which is weaker? This one is weaker. If we look at our bases, remember the base strength goes backwards. The OH is stronger and the PO4 is weaker. So we have, as is usually the case, in fact almost always the case, move this up so you can see, weak reagents on the left, strong reagents on the right. So clearly stronger reagents are more reactive. It's going to move to the left. Okay, so if you have these in equilibrium, the equilibrium will lie to the left. All right, so look at the appendix, or I can give you a quick shout out here with my example. Okay, so there's the table. We're looking for ammonium. Let's just go through and label them. Okay, so that's a proton lost. Okay, and that's a proton gained. Okay, so a proton gainer is a base. That's a conjugate acid. So this guy here then, lost, that's an acid, that's a conjugate base. So we can choose what to look at first. Let's look for ammonium and ammonia. All right, sorry, let's get this straight here. Let's look at the acids, right? Who's weaker, who's stronger? So ammonium and water. Ammonium and water. There's water, there's ammonium. Ammonium is stronger, okay? Strong, weak. Okay, bases, who's stronger? OH or NH3? Remember, strongest at the bottom, OH is stronger. Stronger, weaker. So, remember, you have the power of the pause button, okay? You can pause at any time. I suggest now if you need to work on it a little bit. So look at that. Remember, we're going to have the strong reagents react. Which direction will that equilibrium move? Okay. All right, so clearly it's going to move to the right because strong reagents will react. Okay, so again, that's from the appendix. It's a much better table than the one I have in the notes, and you can refer to that for questions. All right. Moving forward, we get to a very interesting concept, the auto-ionization of water. Okay, now, just as a bit of background here, if you think about it, every single chemical reaction we see in a test tube is probably happening in an aqueous solution. In other words, we have things that are dissolved, reagents dissolved, and they're actually being moved around and bumping into each other using water as a solvent. And that's fantastic, okay? Water is the so-called universal solvent, okay? Now, it turns out that water itself can dissociate to form products, and here's the equilibrium right here. Now, what have I got a picture of someone biting their nails? Well, there is a word in the English language, and this is kind of a joke. It's called auto-cannibalism, which literally means to eat oneself, right? Auto-cannibalism. And so when you bite your nails, you can be psychologically diagnosed with auto-cannibalism, which is kind of an extreme way to think about it. Now, eating oneself, auto-cannibalism, auto-ionization is self-ionization, okay? So when we have water, it can break apart to make H plus and OH minus. If I do that a little bit more simply, okay, maybe in terms of something we've seen, you know, on a more kind of everyday level. Remember, we can write H2O, H plus and OH minus. Remember, yes, we have truly the hydronium ion, but we always write the hydronium ion, wink, nod, you know, nudge, nudge, wink, wink as H plus, right? So really, you know, this is acceptable, although that's what you'll see in the book. Okay, so water can split apart to make H plus and OH minus. And the question becomes, well, do you think that equilibrium lies to the right or left? And common sense says that absolutely 100%, well, not 100%, 99.9999% lies to the left, because a glass of water is mostly water molecules. It's not super acidic or super basic, right? Okay, so having said that, and we get this idea that the K value for that's really small, there's lots of reactants, hardly any products, it is measurable. Okay, so what we're going to do is write a traditional equilibrium expression. So K equals products, and we use the big equation at the top there. Products, H3O plus, OH minus over H2O squared. And that's what you'd write traditionally, right? That's what you'd write traditionally. Now, it's a little bit silly because, you know, water is actually a liquid here, right? Which has no real kind of discernible, calculatable concentration. I mean, what's the concentration of a pure thing? It's undefined, yeah? So what we can do, we can collect this constant with this one and do that same thing we've done before, right? So I'm going to say, hey, K times H2O squared, and that's a new constant, equals H3O plus OH minus. Let me move this up for you. All right, fair enough. So this constant, we can just redefine it. We'll call that KW. W for water, of course, right? Equals H3 plus O OH minus. And you know, if you just want a kind of the more simpler form, H plus, OH minus. Now it has a measurable value, 1 times 10 to the minus 14. So yeah, the concentration of the products multiplied is 10 to the minus 14. Okay, so Kw is a super small equilibrium constant. All right, so look down here, I'll pick it up. A little hokey, but I'll pick it up. So Kw is 10 to the minus 14, which equals in any solution, so this equilibrium is always in the background, any aqueous solution, the H plus ion concentration times the OH minus concentration is this small number, okay? So if they're equals, the concentrations are equal, that's both 10 to the minus 7, okay? And then they would adjust from there. So that's kind of the basis of this work, is using Kw to figure out concentration of H plus, concentration of OH minus under neutral, acidic and basic conditions, okay? So that's kind of an important thing to remember, okay? Now then, now for some fun, okay? If we remember that Kw is always a fixed equilibrium constant, 1 times 10 to the minus 14, which equals 1.0 times 10 to the minus 14 equals H plus times OH minus in any solution. Okay, so if you think about it, what must the concentration of H plus and OH be in a neutral solution? Now here's a kind of stunning revelation, okay? When something is acidic, it still has OHs in it, okay? It's just that the ratio is off, yeah? So when something's acidic, there's more H plus than OH minus. When something's basic, there's more OH than H plus, okay? It's like a balancing kind of deal. And when they're exactly equal, a solution is neutral. So neutral solution, the H plus ion concentration is identical to the OH minus ion concentration. It's interesting, things that are said to be acidic have an excess of H plus, things that are basic have an excess of OH minus. However, there are two concentrations when multiplied always equal a constant. So if you think about it, something that's neutral, what two numbers multiplied together equal 10 to the minus 14? Well, it's 10 to the minus 7. Okay, so the concentration of H plus in a neutral solution is 10 to the minus 7 moles per liter. The concentration of OH minus in a neutral solution is 10 to the minus 7, because 10 to the minus 7 times 10 to the minus 7 is 10 to the minus 14. Okay, so that's true for any neutral solution. Concentration H plus times concentration OH minus always equals 10 to the minus 14. If it's a neutral solution, by definition, these are the same amount, 10 to the minus 7 times 10 to the minus 7, 10 to the minus 14. Okay, hope that makes sense. Now, what is pH a measure of? We've heard this phrase multiple times. pH, right? So pH, we use it all the time, but do we really know what it means? Well, pH is a measure of acidity. Okay, because it's the H in pH pertains to the H plus ion. Okay, so pH, you're doing something with the H plus ion concentration. All right, so if we think about that, at pH 7, the concentration of H plus equals 10 to the minus 7. Oh, interesting. Okay, so pH equals 7, concentration of H plus is 10 to the minus 7. How do I turn this concentration into this pH? How do I turn 10 to the minus 7 into 7? Okay, that's what pH is, and that's what the concentration is. What's the relationship between concentration and pH? Well, if you look very simply, it's just the power with the minus sign removed. Okay, so the power with the minus sign removed, and say we were taking chemistry 100, and maybe if you ever took that class you remember this, your instructor may have just said, hey, just take the power and take the minus sign away. That's the pH. Okay, that works for nice round numbers, and it's true. Okay, but hey, we're Chemistry 102, right? What is the mathematical function that turns this into this? Well, we've got to take the power. That's called log, right? So log. We're going to take the log of the hydrogen ion concentration. So 10 to the minus 7, the log is minus 7. And then we're going to change the sign. And that's what pH equals. pH is the minus log of H plus ion concentration. If you like, the P function, hold this up so you can see. P is just a mathematical function that means take the negative log, and the H in pH is the H plus ion concentration. Okay, so pH, take the minus log of the H plus ion concentration, take the minus log of the H plus ion concentration. Okay, so P is simply a mathematical function that means take the minus log in base 10 of the quantity of interest. So you can do a P for anything. You can do POH even. If you want to take the minus log of the OH ion concentration, you can do that. Okay, and as we'll see, we can do some neat math when we actually do take the minus log of the H plus ion concentration, the OH minus ion concentration, and KW. We get some interesting numbers to play with. Okay. All right. So remember, pH equals minus log of the H plus ion concentration. Good to go. All right. So POH then is minus log of the, you guessed it, OH minus concentration. Now in a solution that's neutral, hey, POH equals minus log of 10 to the minus 7. Remember what we just did? In a neutral solution, concentration of acid equals concentration of base, 10 to the minus 7. Minus log of that equals 7. Okay. All right. pKw, well, Kw equals 10. I'll just do it in scientific notation. 10 to the minus 14. So pKw, take the minus log of that, what'd you get? Equals 14. Okay. So there's your three simple equations. pH is minus log of the H plus ion concentration, POH minus log of the OH minus concentration, and pKw is the minus log of 10 to the minus 14, which is 14. Okay. Now there's a synergy. What does that mean? What's a synergy? As one goes up, one goes down. Okay. So if the pH is very low, the POH is very high because they combine to make a constant. Okay. So if we look here, if I have a pH of 2, I have a POH of 12. Okay? Together, they add up to 14. And we'll see that simple math in a moment. Okay? Just remember this, as one rises, the other one falls because their multiplier is always the same value. i.e., pH plus POH equals 14 always. pH plus POH equals 14 all the time. When the solution's neutral, that's 7 and 7. Say it were acidic, that might be 2, and that would be 12. Okay? That would be a low concentration, that would be a high concentration. Remember, it's measuring a negative power there. A negative 2 power is a much bigger number than a negative 12 power. Okay, so if you do remember your Chemistry 100 or 101, there's the classic pH scale we like to show you. Okay, so we see the relationship now. So at pH 7, the concentration of H plus is 10 to the minus 7. When we have an acidic pH, 10 to the minus 2 is a pH of 2. When we have a classic basic solution, the concentration of H plus is real low, 10 to the minus 12, pH of 12. Okay, so remember, pH scale, we're measuring the concentration or the log of the concentration of the H plus ion. Okay, so the larger the pH, the larger the negative power. In other words, the smaller the value for concentration. Okay, so some questions. I love to ask questions. pH and pOH are strong acids, weak acids, etc. Okay, now if we look at this one, and if you want to try this, this is a great spot to pause. Okay, it's a great spot to pause, try the questions, and then come back and look at the answers. Okay, but what we got here is 1, 2, 3, 4 strong, they're all strong, acids and bases. This is monoprotic, this is diprotic, this is monobasic, this is dibasic. Okay, so we'll see a doubling of H plus concentration and a doubling of OH minus concentration, but remember that will not double the pH, okay, because it's a log function. We'll see a small change in pH. All right, so let's do the first one. HCl goes to H plus and Cl minus. For every one HCl molecule I get one H plus, so I get an equal concentration. So pH is the minus log of 0.055, which equals 1.2, looks like a 6. I can barely read my own writing. Okay, so there we go. So the first one, nice and easy, monoprotic, same concentration of H plus as original HCl, monoprotic. What's the minus log of that? 1.26, which makes sense. Hey, 0.05 mole HCl has a pretty acidic pH. Next one here, H2SO4 turns into 2H plus and SO4, 2 minus. So I'm getting twice the concentration of H plus. I got 2 times 0.055, 0.11 molar. So the pH then is the minus log of 0.11, which equals 0.96. Yeah, we're not familiar with such low numbers, but that's obviously not twice this or half this. It's quite close, but it is a smaller number, it's more acidic. Okay, now it does say pH and pOH, right? Okay, so remember, pH plus pOH equals 14. Okay, so we can do that. So here, pOH equals 14 minus 0.96. What's that? 13.04, right? Something like that. Okay. Do the same up here. That'll be pOH equals 12 point, let's do math in my head, 74. Okay. All right. Here, 0.008 molar NaOH. NaOH turns into Na plus and OH minus. Now here, we've made OH minus. Okay, so be careful. The concentration of OH minus, so we're going to find the pOH, which is the minus log of 0.008, which equals, according to my calculations, 2.1. Well, that's fair enough. Don't be tempted to write that though, because pH equals 14 minus 2.1, 11.9. Okay. You see that one. Finally, dibasic. So I've got 0.016 molar OH. pOH equals minus log of 0.16 equals 1.8. So pOH equals 12.2. All right. Hopefully that makes sense. Again, you have the power of pause and the power of rewind, so feel free to go back. Basically, remember, whatever we're talking about, be it H plus, or OH minus, if you take the negative log of that, you'll find the respective P value, right? So pH, pH. Direct, yeah? If we go and measure OH minus, we'll find the POH and then have to convert it because 14 minus 2.1 in this case. So remember that quick equation? pH plus POH equals 14. So if I want pH, it's 14 minus pH. Okay. Workshop. Small groups. Well, groups don't get smaller than one person, right? So give it a shot. Okay, this is quite similar to what you'll see on an exam. Okay. Find the pH, the POH, and the OH minus concentration for each of these solutions. Okay, so feel free to pause it, come back when you're ready. Okay. All right, so first one, if we have an H plus ion concentration of 0.0041, pH is nice and easy. It's the minus log of that. 2.3. POH then is dead simple. 14 minus pH. 14 minus 2.3, 11.6. Oh, 11.6. 11.7. I guess I did some rounding there. Okay. OH minus concentration. Now be careful here, okay, because if POH equals minus log of OH minus ion concentration, you want this thing, right? So do some math here. So minus and then 10. So OH minus equals 10 to the minus POH. That's worth remembering, which equals 10 to the minus 11.6, which equals 2.5 times 10 to the minus 12 molar. Does that make sense? Yeah, we have an acidic solution, so the concentration of OH is super small. Okay, here we have a super small concentration of H+, and if you look at that, just a quick heads up, 10 to the minus 9. 10 to the minus 7 is that line in the sand for neutrality, where H+ concentration equals OH minus. So we'd expect this to be basic, right? Because there's a much smaller number of H+ than synergic OH minus. All right. So pH equals minus log of that small number. I'm predicting something bigger than 7 because it's going to be basic. And we get 8.4. Very good. POH, we expect a smaller number. 14 minus 8.4, 5.5. Very good. OH ion concentration equals 10 to the minus POH, 10 to the minus 5.5, 2.9 times 10 to the minus 6. Okay, I'll blow that so you can see it. Hope that's making sense. Again, if you feel a little rush, feel free to go through this again. If you've got a question, just post it up in the discussion area and we can kind of discuss as a group, okay? All right. Now, next one, question 3. It's an algebra problem, ladies and gentlemen. It's an algebra problem, okay? So you may be looking at that and thinking, how the heck do I work this out, okay? So remember, H plus times OH minus equals 10 to minus 14. In other words, KW, right? That's KW. Okay. Now it says, hey, the H plus ion concentration is 10 times greater, right? So that means if I call that X, yeah, okay, what do I call this one? Well, I don't know what the numbers are. That would say they're equal. All right, that would say they're equal. All right, but the H plus ion concentration is 10 times bigger. So I put a 10 there. Therefore, 10x times x is 10x squared equals 1 times 10 to the minus 14. Therefore, x equals 3.2 times 10 to the minus 8. All right, so question says pH, right? So pH equals minus log. Now, remember over here, the H plus ion was 10 times that, right? So 3.2 times 10 to the minus 8 times 10. That makes sense. All right. 6.5. If we think about it, hey, 6.5 plus 7.5 is 14, so pOH is 7.5. OH minus concentration equals X, which is this number. 3.2 times 10 to the minus 8. Oh, I'm writing off the bottom. There we go, let me just run through it with you. So the question says, what is the pH, the pOH, and the OH minus ion concentration when there's 10 times more H plus than OH minus? So H plus times OH minus is Kw, 10 to the minus 14. Hey, there's 10 times more H plus than OH minus. So we don't know how much, call it X and 10X, okay? Do the math, 10X times X is 10X squared, which equals 10 to the minus 14. Just moved it around to find X, which is the OH minus concentration, okay? X, which is OH minus ion concentration, 3.2 times 10 to the minus 8. We can just write that in down there, okay? The pH is, well, 10 times that would be the H plus concentration, minus log of the H plus ion concentration is the pH. And we just do subtract from 14 to find the pOH. Hope that makes sense. All right, that's a good one. I like to do questions like that on tests, so watch out for that down the road. Okay, we talked about this already, so I'm not going to discuss it. And then we're at the appendix. Okay, that's the end of your first packet. Don't forget to get back to me and tell me what you think about this work. Okay, if this is working for you, great. If not, let me know how you think I can better enhance your experience. Okay. Now, I'll leave note packets open for as long as possible. So try and complete them just as you would in class, okay? Just as you would in class. And then try the homework after that. Okay. I'll talk to you next time.
High five! Great!
Hi everyone. Here's something fun. So occasionally I like to give you a surprise extra credit. So if you're watching this, okay, congratulations. You have hopefully reached the end of the last video, okay, and here's my happy smiling face, right? If you're here and you're watching this before the deadline for watching this video, send me an email immediately with the line in the title, give me 5, right? Give me 5 points of extra credit. I'm giving you 5 points of extra credit for getting to this video on time. Woohoo! Okay, see you next time.
High five! Great!